Let's discuss transformer load and fixture calculations. We are dealing with a 277 volts to 12 volts transformer rated at 300 watts, with lamps consuming 35 watts each, and tracks holding between 4 and 6 fixtures. Firstly, let's calculate the transformer current on the secondary side. This is found by dividing the transformer's power rating by the secondary voltage. In this case, 300 watts divided by 12 volts equals 25 amps. Secondly, the circuit breaker built into the transformer is rated for 25 amps, matching the transformer's secondary current capacity. This circuit breaker provides overcurrent protection for the secondary circuit. Now, regarding the number of fixtures the transformer can support per track, it's between 4 to 6, depending on the total load. To calculate the total load per track, multiply the number of fixtures by the wattage of each fixture. For example, with 4 fixtures per track, the total load is 4 multiplied by 35 watts, equaling 140 watts. With 6 fixtures per track, the total load is 6 multiplied by 35 watts, totaling 210 watts. Let's consider voltage drop. Assuming a wire resistance of 0.1 ohms per 100 feet, the voltage drop for a 100-foot run of wire carrying 25 amps would be calculated as follows. Voltage drop equals current multiplied by resistance. Therefore, 25 amps multiplied by 0.1 ohms per 100 feet results in a 2.5 volts voltage drop. Finally, the transformer must be properly grounded to ensure electrical safety. Grounding provides a path for fault current, helping to trip the circuit breaker in case of a short circuit or other electrical fault. Proper grounding is critical for preventing electrical shock and minimizing the risk of fire. This covers the essential aspects of transformer load and fixture calculations. It's important to adhere to electrical codes and safety standards during installation and operation. Always consult with a qualified electrician for any electrical work. Understanding these calculations ensures efficient and safe operation of your lighting system. To reiterate the key points, remember to calculate the transformer's secondary current by dividing the power rating by the secondary voltage. This gives you the maximum current the transformer can handle. Ensure the circuit breaker rating matches or slightly exceeds the transformer's secondary current to provide adequate overcurrent protection. Calculate the total load per track by multiplying the number of fixtures by their individual wattage. This helps determine if the transformer can handle the load. Consider voltage drop, especially for long wire runs, as it can affect the performance of the fixtures. Use appropriate wire gauge to minimize voltage drop and ensure efficient power delivery. Always ground the transformer properly to protect against electrical shock and fire hazards. Grounding creates a low impedance path for fault current, allowing the circuit breaker to trip quickly in case of a fault. Remember that these calculations are based on the provided parameters. Actual values may vary depending on the specific transformer, fixtures, and wiring used. Always refer to the manufacturer's specifications and consult with a qualified electrician for accurate and safe installation. In summary, proper planning and accurate calculations are crucial for a safe and efficient lighting system. By understanding transformer load, fixture count, voltage drop, and grounding requirements, you can ensure the reliable operation of your electrical system and protect against potential hazards. Always prioritize safety and adhere to electrical codes and regulations. This ensures the longevity and safety of the electrical installation. Review local and national electrical codes for specific requirements related to transformer installations and wiring practices. These codes provide detailed guidelines for ensuring electrical safety and compliance. Consulting these resources can help ensure that your installation meets all applicable standards. The NEC, or National Electrical Code, provides comprehensive guidelines for electrical installations in the United States. Compliance with the NEC is essential for ensuring safety and preventing electrical hazards. In addition to the NEC, local electrical codes may also apply. These codes may have specific requirements that are unique to your jurisdiction. It is important to be familiar with both national and local codes to ensure compliance. When working with electrical systems, it is always best to err on the side of caution. If you are unsure about any aspect of the installation, consult with a qualified electrician. A qualified electrician can provide expert guidance and ensure that the installation is done safely and correctly. Remember that electricity can be dangerous if not handled properly. Always take precautions to protect yourself and others from electrical hazards. Wear appropriate personal protective equipment such as gloves and safety glasses when working with electrical systems. Energize circuits before working on them whenever possible. Use insulated tools to prevent electrical shock. By following these safety precautions, you can minimize the risk of electrical accidents. Electrical safety is everyone's responsibility. By taking the necessary precautions and following established safety procedures, you can help create a safe working environment. Education and training are essential for promoting electrical safety. Make sure that you and your colleagues are properly trained in electrical safety practices. Regular training can help reinforce safe work habits and prevent accidents. Electrical safety is an ongoing process. It requires continuous vigilance and a commitment to following established safety procedures. By working together, we can create a safe and productive work environment. Review the specific requirements for transformer installations in your area. These requirements may include restrictions on the location of transformers, requirements for ventilation, and guidelines for grounding and bonding. Ensure that your installation complies with all applicable regulations. Remember that transformers generate heat during operation. It is important to provide adequate ventilation to prevent overheating. Overheating can damage the transformer and create a fire hazard. Ensure that the transformer is installed in a well-ventilated area and that there are no obstructions blocking airflow. Regular maintenance is essential for ensuring the reliable operation of your transformer. Inspect the transformer regularly for signs of damage or wear. Check the connections to ensure that they are tight and secure. Clean the transformer to remove dust and debris. By performing regular maintenance, you can extend the life of your transformer and prevent costly repairs. If you notice any problems with your transformer, such as unusual noises or overheating, contact a qualified electrician immediately. Do not attempt to repair the transformer yourself unless you are a qualified electrician. The electrical repairs should only be performed by qualified professionals. Remember that electricity can be deadly if not handled properly. Always take precautions to protect yourself and others from electrical hazards. Consult with a qualified electrician for any electrical work. Let's delve deeper into the aspects of transformer selection, load balancing, and power quality. Firstly, the selection of a transformer should align with the anticipated load and future expansion plans. Oversizing a transformer can lead to inefficiency, while undersizing can cause overheating and premature failure. Secondly, load balancing is essential in three-phase systems to prevent unbalanced currents and voltage drops. Distribute the load evenly across all phases to maintain optimal performance and prevent equipment damage. Thirdly, power quality refers to the stability and reliability of the electrical supply. Harmonics, voltage fluctuations, and transient surges can negatively impact sensitive electronic equipment. Install power quality filters and surge suppressors to mitigate these issues and ensure a clean power supply. Let's elaborate on the practical aspects of transformer installation, commissioning, and troubleshooting. Firstly, transformer installation should be performed by qualified electricians in accordance with manufacturer's instructions and local electrical codes. Ensure proper ventilation, grounding, and overcurrent protection. Secondly, commissioning involves testing and verifying the transformer's performance before putting it into service. Perform insulation resistance tests, turns ratio tests, and polarity checks to ensure proper operation. Thirdly, troubleshooting involves diagnosing and resolving problems with the transformer. Common issues include overheating, voltage fluctuations, and equipment failures. Use appropriate testing equipment and follow safe work practices when troubleshooting. Transformers play a critical role in electrical power distribution systems. Their efficient and reliable operation is essential for ensuring a stable and safe power supply. By understanding the principles of transformer operation, installation, and maintenance, you can maximize their performance and prevent costly problems. Remember to always prioritize safety and consult with qualified professionals for any electrical work. Let's discuss the importance of preventive maintenance for transformers. Firstly, schedule regular inspections to identify potential problems early on. Check for oil leaks, corrosion, and loose connections. Secondly, perform insulation resistance tests to assess the condition of the transformer windings. Low insulation resistance indicates potential insulation breakdown. Thirdly, monitor the transformer's operating temperature to detect overheating. Overheating can shorten the life of the transformer and lead to premature failure. Fourthly, clean the transformer regularly to remove dust and debris. Dust and debris can insulate the transformer and cause it to overheat. Fifthly, lubricate moving parts such as fan motors and tap changers to ensure smooth operation. By implementing a comprehensive preventive maintenance program, you can extend the life of your transformer and prevent costly downtime. Let's explore the advanced concepts of transformer design, operation, and control. Firstly, transformer design involves optimizing the core material, winding configuration, and insulation system to achieve desired performance characteristics. Secondly, transformer operation is influenced by various factors such as load conditions, voltage fluctuations, and ambient temperature. Thirdly, transformer control systems can be used to regulate voltage, current, and power flow. These systems can improve the efficiency and stability of the electrical grid. Let's delve into the details of transformer protection schemes. Firstly, overcurrent protection is used to protect the transformer from excessive current flow due to overloads or short circuits. Fuses and circuit breakers are commonly used for overcurrent protection. Secondly, differential protection is used to detect internal faults within the transformer. This protection scheme compares the current entering and leaving the transformer. If there is a significant difference, it indicates a fault within the transformer. Thirdly, sudden pressure relays are used to detect rapid increases in pressure within the transformer. These relays can detect internal faults that generate gas or vapor. Fourthly, temperature monitoring is used to detect overheating of the transformer windings or oil. Temperature sensors can trigger alarms or trip the transformer if the temperature exceeds a safe limit. By implementing appropriate protection schemes, you can minimize the risk of damage to the transformer and ensure the safety of personnel. Let's discuss the environmental considerations related to transformers. Firstly, transformers contain oil that can be harmful to the environment if spilled. Implement spill prevention and containment measures to prevent oil spills. Secondly, transformers generate noise during operation. Install noise barriers or enclosures to reduce noise pollution. Thirdly, transformers consume energy during operation. Use energy-efficient transformers to reduce energy consumption and greenhouse gas emissions. Fourthly, transformers can be recycled at the end of their useful life. Recycle transformer components to recover valuable materials and reduce waste. By addressing these environmental considerations, you can minimize the environmental impact of transformers. Remember to consult with environmental regulations and best practices for managing transformers in an environmentally responsible manner. Let's explore the economic aspects of transformer ownership. Firstly, the initial cost of the transformer is a significant investment. Select a transformer that meets your requirements and budget. Secondly, the operating cost of the transformer includes energy losses, maintenance, and repairs. Minimize operating costs by selecting an energy-efficient transformer and implementing a preventive maintenance program. Thirdly, the life cycle cost of the transformer includes the initial cost, operating cost, and disposal cost. Evaluate the life cycle cost to make informed decisions about transformer selection and management. Fourthly, consider the potential cost of downtime due to transformer failure. Implement appropriate protection schemes and preventive maintenance programs to minimize downtime and associated costs. By considering these economic aspects, you can optimize the total cost of ownership of transformers. Let's look at advanced topics such as smart transformers and solid-state transformers. Smart transformers incorporate advanced sensors, communication capabilities, and control algorithms. These transformers can monitor their own condition, communicate with other devices, and optimize their performance. Solid-state transformers use power electronic devices to perform the functions of a traditional transformer. These transformers are smaller, lighter, and more efficient than traditional transformers. They also offer advanced features, such as voltage regulation and power quality improvement. These advanced technologies are transforming the electrical grid and enabling new applications.